Good evening and a warm welcome to this lecture. My name is Robert Dijkgraaf. I'm the director of the Institute for Advanced Study, and this warm welcome is certainly for, I see many familiar faces, but actually this warm welcome is also particularly directed to a very special group that we actually are welcoming here this week and next week at the Institute, which are the participants in the Women in Mathematics program that the Institute has now been running for many, many years. And it's one of our activities, academic activities that we're very proud of. It's an opportunity to bring women mathematicians at various institutions, at various stages in their career, together, from the undergraduates to graduate students to people teaching at smaller institutions, larger institutions, very experienced lecturers, all having fun doing math, and this is, I see many faces here who have played an important role. I want to recognize Karen Uhlenbach, you've been key to it. Christine Taylor, that's actually doing a lot of work and is leading the effort. And this is, I think, a terrific way in which certainly, I think, I just noticed that the Institute these 2 weeks looks even more cheerful than it does. But also we're blessed with wonderful weather, and it was great to see all of you out on the deck chairs in the lawn and enjoying the Institute. Now, of course, this is a terrific opportunity to support mathematics. Support academia. As you know, the role of the Institute not only to bring scholars here and make sure they do the best work in the best circumstances, but we also feel that we have a larger role in life, and that this is one of the ways we reach out to a larger community, and we hope that this really is supporting mathematics in a very powerful way. The program is quite varied, from problem sessions to guest lectures, and so we arrived here at a high point of the week, which is a great pleasure to introduce tonight's speaker. She's Claudia Perlich. Actually, Claudia and I met a few months ago in a kind of a terrific dinner that I was pleased to be introduced to, which are some sort of the crème de la crème from the data scientists in New York City. And just noticed that there was this kind of terrific link between mathematics and the work that you are doing. And I think actually this could be, for many ways, for us, an eye-opener. Claudia has been the chief scientist at Dstillery since 2010, where she designs and develops optimal machine learning systems that identify prospective customers for her clients' brands and targets them on online display ads. She previously worked at the IBM Watson Research Center on data analytics and machine learning. In some sense, it's very appropriate that you are coming here. Because, as you know, of course, the Institute played an important role at the founding moments of computer science with the work of John von Neumann. For those of you who are not aware of that story, I think most of you are, that von Neumann built basically the first programmable computer with the von Neumann architecture here. And the Institute had kind of dubious feelings about that, in the sense that now, of course, we're incredibly proud and we highlight this, but actually at that time, there was mixed feeling, because this is a place of deep thought and not really experimental and engineers. And at some point in the 1950s, there were more than 30 engineers actually working on that computer. And it was, and in some sense, this was quite an experiment. And I think the thing I learned from this, it's from your experiments actually that you afterwards are most proud, and you see new perspectives. Claudia actually came to the US as an exchange student, I think in 1995. She grew up in Eastern Germany, in East Germany, where her father was working on an effort to build replicas of some of the IBM machines, I understand. She came here as an exchange student, to following basically in her father's footsteps with computer science, an area of study. She kind of fell in love with data during a course in artificial neural networks in Boulder, Colorado, and she went on to complete her MA in computer science in Boulder, and then her PhD in information systems at New York University. I think now she's right in the midst of a very exciting development that we, of course, read about every day, but which also has very deep kind of mathematical roots. And so I think we're all quite excited to learn that new field. It certainly will be an important part of the future to all of us, but particularly I hope for those who are here in our program. So I hope you join me in welcoming Claudia to the stage. And I should add that she likes this to be as interactive as possible, so interrupt her at any moment.
First off, I really wanted to thank Robert and the organizers for having me here. It's a great honor to be at a place of such history and influence. And also, I never get to speak in front of an audience with at least half women. Never happens. So this is a new one. I feel a little bit disturbed right now here. So I do hope I will have some time afterwards to interact with most of you in more detail. But talking of interaction, it's more fun for me if you ask me questions, and if you have anything you want me to go in greater depth or less depth, then by all means interrupt me. I like the conversations around it, and we can certainly have some follow-ups afterwards. I also put the old name of our company. We used to be called Media 6 Degrees. Anybody, any idea what Media 6 Degrees might be? It comes from the experiment of the 6 degrees of separation, where letters are sent to a totally unknown address, and on average, or the median technically speaking, it took like 6 handovers to deliver letters just person to person to person until they finally found their way. The company was founded about 6.5 years ago, originally focusing on social, but eventually now I will tell you that it's really just machine learning, and I'll give you probably more detail than you ever wanted to know about advertising in the process. So Robert already gave a very nice overview of my background, so I have kind of summarized it here. When I grew up, I was reasonably good at math, but I wasn't great, let's face it. I mean, top of my class, yes, but nothing to go really into the field. So when I finally had to make a choice about what to do with my life, I decided for computer science was primarily to really delay the problem, because it felt like, well, they will use computers everywhere, so, you know, maybe in 3 years I know what I want to do with my life. And besides, my dad was in the business, so it felt like he supported the idea. And I went to Colorado, somewhat spur of the moment, that wasn't really planned, and also more or less accidentally came to this course on artificial neural networks and just got hooked on data. So from there on, there was no back. I was never really that interested in abstraction. I like things real. I like to solve puzzles and problems that are very concrete. That was already why I chose computer science over math, and it's now that I choose data and its application over more theoretical fields of computer science. Then I applied for PhD programs, and somewhat accidentally, again, out of computer science into a business school. And I remember Andreas, my friend and mentor, asked me, why don't you apply here? I said, it's a business school. I know nothing about business. Now, he's a PhD from Stanford in physics. And he told me, it's not a problem, neither do I. So I find myself in a business school, yet again, more applied problem solving than most computer science departments are. And after that, I joined IBM Research, Watson. I had a really enjoyable time there, great colleagues, and I learned a lot about practical problems, kind of grew into myself, so to say. And one of my claims to fame in the data science world is I used to participate in these data mining competitions. You might have heard of the Netflix competition where you could win $1 million. They were kind of precursors of those. I used to do them. These days I organize them. But talk to me if you want to know a few tricks about it. And then about 5 years ago, I was asked if I was interested in trying out kind of the complete opposite startup situation. And it was just an incredible opportunity to see what you build being used within a matter of days and weeks. So being at the forefront and having access to data that was unparalleled. And so even today, it is advertising technology is kind of the sandbox of anything you ever wanted to try out with data. It gives you the opportunity to explore, learn, research, and see what works and what doesn't. And then I still teach at NYU in the MBA course and try to share some of these knowledge that I have acquired. So much about me. Let's talk about what I actually do. There's really only one thing I'm good at, and that's build predictive models. Now, who has heard about predictive modeling? Who knows about predictive modeling? All right, so we have some background. Let me kind of give everybody else the very simple way of looking at it. For me, it's basically function approximation. You start with data. I give you a whole bunch of data. And the task is, can you find the best function that represents that data? So you don't start from first principles necessarily, but here's data. There's a quantity you're interested in. Let an algorithm, and a lot of math, which I'm not even going to touch on, come up with a way of extracting a function that best represents this. Now, this stuff is not new. The algorithms are certainly not new. The applications are everywhere in your life. Your spam filter, blame it on an algorithm that may not get it right all the time. There is a lot of it being used in financial trading, fraud detection, all of the recommender systems, who is recommended as your new friend, the job you're being recommended on LinkedIn, all this is driven by technology that learns from data. And one of the areas that uses a lot of it is advertising. So how does it start? Well, I said I need data. So in advertising, we have some information. That's a simple example here. This is where it all begins. You have examples of people, you have some information about them, and then there's an outcome. Whether or not somebody responds to an offer, whether a specific email is spam, whether a particular medical claim is fraud. You have an outcome that you really want to know about. You want to predict what is the probability that here a person responds. So I'll give it to my computer. This is a very simple two-dimensional problem where I can still show it to you. And one of the oldest kids on the block is logistic aggression. It's an algorithm that was invented early in the last century, so this is not new data science either. And basically what it says is, let's just assume some functional form. I mean, we have to start somewhere, right? So logistic aggression says, I believe that the world is kind of linear, that the probability of the outcome has this linear structure. And what the task of the algorithm is then is to take a look at the data and find the best linear function that represents the data. And off the computer goes basically estimating the parameters in this equation. And in the end, it tells me, here are the parameters. Now the equation is done. If I need to predict for a new entity, person, well, I run it through the equation and I'm getting an answer. The probability of response being 1 is given to me by the resulting equation that came from the algorithm. There are probably 1,000 different algorithms out there. Logistic aggression is one of them. There are many, many ways to do that. I'm not going to talk about it. Just assume there are these things that build it. There are long-standing debates between academics on which one is the right one and the best one, and they're proving one thing and the other. My personal favorite is one of the oldest, logistic aggression. I picked it for a reason. Again, those of you in machine learning, we can have a heated debate about the relative advantages later on. So that's my day job. How many ads do you see? At least 4, there might be 5, I'm not sure. So advertising everywhere in your life. Today, it interacts with you in real time on your apps, on the websites you go to. And I'm one of those you can blame for seeing these things and whether or not they fit your taste or don't. So how does it work? This is my mom. She's one of the 200 million browsers who hasn't figured out yet how to disable third-party cookies. Which means I can collect data on her behavior. Now, when she's reading in the internet, say she goes to the New York Times, what happens if there is a slot available for an ad? That slot, in real time, is sold in an auction. There are so-called ad exchanges, and there are many of them. Google owns one, and Facebook has one, and many, many more. And from this ad exchange, it comes to me. And we get about 20 billion of those in display, another 20 for mobile ads every day. And I have some amount of time, typically about 100 milliseconds, to make up my mind whether or not I want to bid on the opportunity of showing that person an ad on that site. I can submit my bid, and if I win, I get to put the ad. Now, what do I know at the time? This is where all that data comes back. I don't know it's my mom. But I have assigned her a 20-digit identifier. It's like a random number that becomes your, quote unquote, it's the social security number you have with me. Like, I give you a number until you delete the cookie, then you get a new one. And so it goes. So how do we collect data? Well, we get this information, so we get the ID of the person that we are currently bidding on, but we're also collecting data from other data providers. So when people browse more generally, we have agreements with data partners that put what's called a pixel on the website, which really just means I can write a cookie on your computer, unless you disable third-party cookies. So that allows us to do this identifier assignment, and then every time you go to a site, I can append a browsing history, so I can keep track of the sites I've seen you at. Now, so far, I'm only paying, right? Where's the money coming from? So people pay us, and when I say people, we're talking about advertisers, brands, or ad agencies, to run campaigns for them. So say Nike comes to us and say, hey, we want you to run a campaign. And the first thing we're going to say is, good, we want a pixel on your homepage too, or on your checkout page. So we can see not only what people do in general, but I need to know who are the people who buy from you. So now we can track that part as well. And then we also agree that for the kind of performance of the campaign, we are going to track what we call post-view conversion. So I'm not interested in predicting who will click on ads. If you predict who will click on ads, you find people with eyesight problems who lost their reading glasses, various fine motor control problems, or people using the flashlight app, fumbling in the dark. If you actually want to show ads to people that are interested in the offer, what we are much more interested in is whether after seeing the ad you actually buy the product. And it doesn't have to be right away. It could be what we call a view-through conversion, which takes like 7 days or whatever time frame people assign. Any question about the super high-level view on how this whole thing works? Yeah?
Do you have a way of determining it's the same person at 2 different websites?
Yes, that's the whole point. I can have a cookie, and that cookie has that 20-digit number I assigned to you, and I can read back out that 20-digit number. The whole point of the cookie and the 20-digit number is to know it's the same you. I don't know who you are, but it's the same.
So it's your company's cookie via the other websites?
It is my cookie on your computer, yes. That lets me, every time we interact, we just read out the number and we store what we see you do actually on our servers. But that's kind of technical details.
But it's not a New York Times cookie or the blogger cookie?
I cannot read the New York Times cookie. So the rules of the cookie world is you can only read your own cookie. I can...
But I didn't go to your website either.
No, you don't need to come to my website for me to have a cookie on your computer, which is this third-party thing. This is the kind of the forwarding that happens through data providers.
So if you have a cookie on my computer, can you see all websites I'm going to, or only if I go to websites where you have a cookie?
So the question is, what does the cookie allow me to see? The cookie only allows me to see when you come to a website that I have the right to look at. So I don't know all the things you do. I have no idea what you do on Facebook. And I have no idea what you do on Amazon or eBay or many of the other walled gardens. I have kind of a partial view of your browsing history. All right, so let's keep going and figure out what we can do here. So what are the problems that I'm working on? Well, there are a couple of key questions that I and our company is trying to answer. The first obvious one is like, who should I target for this product? Right? How do I pick the right person? The second question is, when and where should I show an ad? Because I might know this is the right person, but there are different opportunities. I get these bid requests all day long. One might wonder whether it matters at all. Actually, very few people in advertising really want to know whether it matters, but I'll take a look at it nevertheless. What is a fair price of data? There's a lot of talk about big data, but how much do you really want to invest in that? We have to pay for our data, so it's kind of every quarter we have to contract, we have to renew the contract, and we're being asked, do we really need this stuff? Is it any good? And finally, there was a good reason why the cloud down there is black. As any open market, you very quickly see some unsavory characters trying to extract some gains here, so we do a lot of fraud detection as well. I'll talk about this in the end. So let's take a quick look at the data. What do I collect? To some of the questions being asked before, I don't want to know who you are. I really don't want to know who you are. And I don't want to know where you live, and I don't even want to have to describe you in any meaningful way. All I want is create this browsing history, and we're going to hash it. So the URLs that come in, that could have been a blog about the New York Marathon, get hashed in these obscure strings. Because you know what, in machine learning, the machines don't understand what it means anyway. For them, there's no difference between a meaningful string and a non-meaningful string. It's all the same to them. On the upside, it's somewhat privacy-preserving, and you can rest somewhat assured that I don't really know what you did last summer. We also record the action you take for the campaigns that we're running, but they are kept separately. So they're kind of two sides of the data. One is the stuff we can use for everything, and one is data that belongs to the marketer that I can only use for the marketer, because I can't use the Audi, let's say, data to run a BMW campaign. I mean, you can do this once until somebody figures it out. So there is kind of a separation of what data we own and can use and what data we only borrow for a specific campaign. So we started here, right? Anybody starting to see the analogy to this thing? Well, it's not looking like this. What it actually does look like is like that. I'm tracking basically the order of 10 million different URLs. And it's very, very sparse because any given cookie or person only goes to a very small subset of them. Right? So I just have an indicator in there if you went to this URL or not. People always ask me, doesn't recency and frequency and time since I did? Yes, maybe it matters, but for now the problem is bad enough as it stands, so I'm not dealing with it. And then you have some number of previous purchases that you can try to optimize to. So now we are back in the boat of function approximation. I need to learn how does this, meaning the ones over here, depend on all that, so I can predict it in the future. So basically, same thing. The only problem now is I can't show it in 2 dimensions anymore. And practically, I am no longer estimating 2 parameters, but a couple of million. Now, this is really where the world has changed tremendously in the last 5 years in terms of our ability to scale learning algorithms to these kind of dimensionalities and get away with it. It's still not easy, but it's possible. And I'm happy to take debates later on into how exactly it. I give you a little bit on the background as we move into here. So to summarize, what I would like to do I need to know whether you're interested in buying the product, because showing you some ad for something you really, really, really don't care about is probably not very smart. Doesn't matter how many ads for scrapbooking you're going to show me, I'm not going to buy any scrapbooking material because I don't scrapbook. So I'm trying to find out, like, what is the probability that you're going to buy this, given all the information I've seen about you, like your browsing history, and that I showed you an ad. And new means I'm trying to do this for new customers, because it's very easy to find people who already bought scrapbooking supplies. The much harder problem is to find new people for a given product, what we call prospecting. Now, here's the problem. This is basically not solvable. Not in the mathematical meaning of the term, just in my term. It's something I can't do. And the reason I can't do it, A, the dimensionality is too high. That's not even the biggest problem, but I get very, very few positives. I have very few examples of somebody actually buying something. That makes this function approximation really hard. And to make matters worse, well, at the beginning of a campaign, I haven't shown any ad to anybody yet, right? So I actually have no real example at all, because I haven't done it yet. I don't know who buys after seeing an ad. So I first have to show a lot of ads in order to collect data to then learn something that I can use to show ads. So we're going to cheat. The good news is in machine learning that actually is a whole sub-study of the field. It's called transfer learning. You're trying to solve a different problem than the one you need to solve, but a different related problem. So for once, cheating is okay. Instead of trying to learn something of this purchase, given all that stuff, let's just trying to learn who, without an ad, would have shown any interest in that product. And it doesn't even have to be purchase. It's good enough if you go and read about it. There are a lot more people reading about it than actually buy online. So we're going to build a model we learn from data for a slightly different problem than we really have to solve. And here it turns out I can do that long before running campaigns. I don't have to show ads, right? I can just run it through the machine and build me a model prior to having to show ads, and then use it in the beginning. And what's the transfer here is, I'm not just going to look at new purchases, but I'm looking at anybody who ever showed any kind of interest in this thing, in order to get enough positives to get away with the learning problem in that dimensionality. Technical details, bias variance trade-off, it's a very interesting subfield. I prefer a biased, meaning potentially wrong model, over a high variance, meaning the estimate is different every time I change the data set a little bit. So I prefer to err on the side of bias rather than variance, and having more positives reduces variance, but increases bias, because it's kind of the slightly wrong thing. So it's not really true that I know that you really don't care about the product, but everybody else who hasn't shown any interest yet is a good enough guess for me of you're really not being interested. Again, technical detail, there are ways of correcting the cheating. This stuff is called, in the context of transfer learning, stacking, where it means you build one model that feeds a prediction into another model. So we don't just do this once, but we kind of have cascades of these models learning from each other and kind of changing the information slightly to fix some of these things. Which brings it back to my favorite tool and good friend and buddy, Logistic Aggression. To the statisticians in the audience, it would still sound, or should still sound, pretty scary if I tell you I want to estimate them in 10 million dimensions. This is not really what people like to do. So all kinds of kind of tricks in there, and this is where the optimization has a very strong mathematical link here. People use stochastic gradient descent. There are constraints put in, so it doesn't just count that the model is good. I also want a model that's simple. Simple meaning I don't want really 10 million parameters. I want most of these parameters to be zero. And the way to get there is to put what they call an L1 penalty. So you put a penalty term if just kind of the sum of the absolute values of the parameters that goes into the optimization and makes a lot of them go to zero. technical details, learning rates, how much you upgrade in the stochastic gradient descent. There's a way to initialize the models to a good initial place instead of starting from scratch altogether. And finally, and this is from a privacy perspective interesting, I'm not trying to rebuild the model from scratch every time. Just take the model from yesterday, look at today's data, and update the parameters of the model based on the new evidence. So I don't have to kind of build it over and over and over again. This process is fully automated in our company, and we build on the order of 10,000 models per week. Now, to give you a comparison, in the old days when I worked at IBM, I would spend personally 4 weeks to build one model. Now, it's a system that automatically learns these things. We only have like 7 data scientists. We can't even look at the process anymore. So this is kind of the advancement that technology has brought over the last couple of years. And then, if you want to think about it, what is a model? It's really just these 10 million or 1 million, depending how many are left. After all, most of them went to zero. Parameters that indicate going to the website seems to suggest that you're interested in the product. For instance, going and reading a blog about the New York Marathon could mean that you're a runner, and could mean that you're actually interested in running shoes, except that I don't need to decide that. It's the model that found it out, that assigned to the hashed ID for that URL of that blog some positive coefficient that then is used for the prediction. Was that a question? No. So I meant it. You can interrupt me anytime you want. All right. So I'll keep going. So what happens with these models? What do we use them for? Well, once I have a model like this, I can score every single one of the 200 million cookies that are floating through our system. When I say score, I can predict for every single one of them. What is the probability that they are interested in any one of the maybe 300 or 1,000 more detailed products that we are currently running campaign for? So now we're using these models and we track people over time. Every time I interact with the cookie, I update the predictions for all the models we have in the system. And if you score high enough, meaning your probability of being interested in this thing, we kind of say, okay, from now on, when a bid request comes for that 20-digit random number, I will bid for that cookie to show an ad. So this is how the model is being used. I constantly predict, and once you get into like the first percentile, like if I rank the whole world, I'm just looking at the top 1%, for bigger campaigns, maybe the top 5%, then I'm starting to bid. This is the pause for you to ask questions. Yes? Good. So the question is, in this kind of 100 milliseconds that I have to make up my mind, what do I actually see? Yes, I see your cookie. Now, your cookie only contains the 20-digit random number. I'm only going to pull that number from your computer, and then I look up on my side, on my computer, in these very large kind of NoSQL systems, all the stuff I know about you, and in particular, what you currently qualify for, meaning which of the campaigns you are ranging in this top 1%. And that feeds the decision whether or not to bid.
What does, I mean, you're saying top 1%, top 5%, what sort of probability of being interested, whether it's probability of having visited the site before or probability of buying something, does that translate to, roughly?
I couldn't care less.
Okay.
It's irrelevant. I have a budget. I need to show 3 million ads for Nike a day. I pick the top N% subject to get to 3 million ads a day. So it's completely irrelevant what the probability is. In particular, I was kind of lying. I pretend that I'm estimating probabilities. I'm actually only really trying to estimate the ranking. I don't need to know the probabilities at the end of the day. So her question about what the probabilities typically are, it very much depends. For pizza, actually it could go up to 10% on the very top. For luxury cars, e to the -8 on a good day. So,
So this is departing a little bit, but then you work with email campaigns and that sort of thing, and then the click-throughs there increase.
right, so the question was, what about email campaigns? Now, email campaigns are different because all of a sudden you know who the person is. Now, could I do good email campaigns? I sure could, but that's not our business model. And besides, I really don't want to know who you are. So this is a business we have been staying away from until now. Would this work for email? Absolutely. No reason not.
Seems that there's been a change away from the static web to many more secure sessions and dynamic URLs. Doesn't that blow up your ability to score what people are looking at?
So the point from the audience here is with dynamic websites that aren't, like, you don't have a static URL, but it's dynamically created, what happens? Sure, it's not helping me. Good. But, you know, we're on the same boat, so it doesn't really, like, it's all about how well somebody else can do it rather than me. But the point is, I didn't really tell you how we hash the URL. What typically happens, we hash it multiple times. So I take the full URL all the way, maybe scrapping the parameters, and then I do it again until one level up, and again all the way to the host name. At the very least, the host name is static, kind of, most of the time. So I give the model the best I can. With dynamically created URLs, I lose fidelity, but you know, I'm in the satisficing business. I don't have to get it right. I just have to get it better than somebody else.
I guess related to that was accountability and how you sort of measure how well your decisions are worked. Do you have holdout samples that you look at, or how do you kind of...
Good. So the questions about how good does this work and accountability. We measure internally how well we can score people probability of taking some action. I'll show you some numbers of that well. Now, obviously, we're also being held accountable by the people who we run the campaign for. So they typically measure conversion rates or implied CPAs or things of that sort, cost per acquisition, meaning how much budget do they need to spend with us relative to the number of people who then buy. It's a huge problem because guess what? I'm not the only one showing you ads. There are a lot more out there. So when you buy something, you probably have seen 15 ads from 10 different vendors prior to that. So the accountability internally is easy for me to evaluate my models. Externally, it's really, really hard because of this whole attribution, which is a mathematically really difficult problem. We can spend evening on this conversation. There was one more, unless it was the same question. Yeah?
So is your data, say, again, make it real simplistic, Coke versus Pepsi. So you work for Coke, you get all of this analytical data, your contract ends with Coke. Can you go to Pepsi with the same data, or is it non-transferable?
Oh, I can do it at the same time. I said earlier, we have two types of data. We have data out of what people do all the time online. That data is not owned by Pepsi, and that data isn't owned by Coke. The blogs you read, the news stories you look at, none of this is owned by either of them. The only thing they give me is that label on the target variable. So now I know who bought Coke, although Coke and Pepsi are terrible examples because I never see when people buy a Coke because it doesn't happen online. But for the sake of argument, that label about the fact that somebody bought the product, I cannot use for anything else than the target variable in these models. So they cannot become information that fuel any decision about any other campaign. And in that sense, like, it's almost like a Chinese wall. Like, we build all these models separately, but we in particular can do it for competitors at the same time.
You also said that one of your challenges was just the very low incidence of actual purchase transactions. So looking one step ahead, you know, rumored that Apple's coming out with a new mobile advertising platform. Wouldn't be surprised if it includes some link of Apple Pay transactions to advertising opportunities. Does
So the question is, as I mentioned, it's really difficult, like advertising luxury cars where you sell, I don't know how many thousand a year. I don't see this, the harder problem isn't so much the tracking and the Apple ID, it's actually the offline purchases and who knows something about offline purchases. I'm not sure if Apple brings that in the mix in any meaningful way, but there are currently already ways. I can tell that you were at a car dealership because I saw your mobile phone. Because you were playing something, and guess what? I showed you an ad. So I got a bid request from your mobile phone from a lat long that I know happens to be a car dealership. That's already something that is happening, realistically speaking. In addition, you can go and buy data from Kantar and other vendors who have the scanner data from people who share that about what people bought 5 packs of Chobani yogurt, for instance. So people are looking into ways of getting more information. I still think we're in a world where tracking offline purchases is guesswork at best. I don't know what what that particular thing is going to do. All right, last one, and then we're going to move on. Excuse me? Oh, mine? Yes, I do. So I selectively disable third-party cookies. Eventually, I got so bored with it. If you actually check how many times somebody requests a cookie on your computer, it's staggering. If you actually look at the list of how many cookies there are, it's quite impressive. But I have found that living with cookies is easier than living without cookies for the most part. Because once you disable the wrong cookie, it gets really difficult to get something done on your computer. So I'm not saying that this is a good thing or a bad thing. You can disable them at your own peril or leave them on. I mean, I take no side in this discussion. All right, let's actually move to a little part that I wanted to talk quickly about, what happens at the bidding time. I know you are a great prospect for a pair of running shoes, or I've concluded my models tell me that you're on the top 1%. Now, does it matter when I show you the ad? Now, first of all, does it matter whether you see an ad at all? That's the first. Once you conclude that ads might actually do something, then maybe it matters where I show them to you. So we have another layer of these predictive models that try to estimate the marginal impact that the inventory where you see the ad has and how that affects my bidding. And what we're going to do here, we're going to estimate 2 more of these predictive models that estimate the probability of conversion given who you are, and S encapsulates all that prior knowledge that the other models have given me. And the current site, whether you're on the New York Times or maybe I got a bid request from your Yahoo Mail account when you're sitting there waiting for mail. And I'm looking at kind of the relative performance, like the probability of conversion given this piece of information over all other possible values, like over the expected value over everything. Turns out it's very easy to get away with expected value calculation. You just delete that attribute and all is good. And so here I'll show you some results for a hotel chain. Not surprising, if I get a bid request from Kayak, much better. Although it's the same person, it's really the marginal impact. If you're on a social media site, apparently you don't need hotel. So this is another layer of intelligence that uses predictive modeling to change the bid price in real time. And somebody asked about the performance. This is not a very recent, but I think comparable. You see on the right axis is what really matters, the lift. Lift means out of the people I chose in my top 1% or whatever, how many of them converted relative to the base rate of just anybody converting. So like, what's the base probability across the whole population? And you see that the models typically do, so it goes down to 1, which means the model does nothing. But for a number of models, you can get very, very high lift. So the model can, the machine learning finds very clear signal of purchase intent and can select this 1%. This doesn't mean that I changed your behavior. It just means that I can find the people who then buy something, which will bring us to the next topic. So this is to the KPI. This is one of the things we are tracking. This is actual campaign. So that's post-view conversion. That's not just in our books on the machine learning. This is actually running the campaign, comparing it to a control group that was not specifically selected by the algorithm, and see how much better the conversion rate is. Does it even matter? Do you buy something because you see ads? Do ads change behavior? So that's actually one of our more intellectual kind of quests that we took on, because, as I said, surprisingly few people in advertising really want to know. No, they don't want to know when they don't work. Everybody loves to hear that it works. I'll take this back. It's a conditional statement. Now, how do you measure causal impact? So far, if you listened well to me, I only promise that I can predict whether you will buy something anyway. I didn't say anything about me making you buy. I didn't say anything about finding people who, because of the ad, are going to buy. So what you can do, and it's kind of an A/B test, is the gold standard. You can say, well, let's find the same kind of people that I would have shown an ad to and show them something else, like public service announcement or any other image, which is the way this usually works. Now, it turns out very few people want to actually pay for this. Back to nobody wants to know. So it's very difficult to convince customers to actually waste impressions on public service announcements. So one really, really interesting area of research right now that gets very mathematical very quickly is trying to estimate causal effect from observational data. A lot of this is happening in the Berkeley statistics department, which is where one of our colleagues is working from. And here the important part is that you need models to predict the counterfactual. I need a predictive model to tell me what would have happened in the other case. Because I can only observe one scenario. Either I show you an ad or I don't. But I will never be able to tell what would have happened hadn't I shown you the ad. And this is where the predictive modeling comes back in to give me that alternative view on the world. So if you simply look at the conversion rate of the people that I selected to show an ad to the people I choose not to show an ad to, it looks great, right? I mean, look at 10% increase here. Or why is that not causal? I picked the people I knew who would buy anyway, right? I mean, I spent the last 45 minutes trying to convince you that I can predict the probability of you buying something. So yes, of course I picked the people I knew who would buy. But I could have shown them a blank and it would look exactly the same. So this is not a causal metric. That's what's called confounding. So my targeting is confounding the causal impact. So please, and this is a bit cheeky, but have fun with it. What does it mean to be confounding? This is Charlie, our intern, and when he's waiting for his queries to finish to get access to his data, he likes to go to a website called Hot or Not, where you can rate pictures. And he likes her. What's the obvious next step here? Well, turns out you can then send them a message. So what the hell do you need to write to get her number? Guys, work with me here, come. So there was a very interesting study by some guy, a data scientist at OkCupid, who looked at that problem. I mean, this is truly useful information, right? And there was an analysis that said, you really shouldn't make any kind of compliments. Now, please don't take this seriously. This is an example of a terrible causal analysis, because this is not what's going on here. The problem is not that because you make a compliment, your probability of getting a reply goes down. The problem is beauty is confounding. If she's truly good looking, she gets a lot of messengers. Your chances of getting a reply are bad to start with. It doesn't matter what you write, they are bad. So making a compliment didn't hurt your chances, it's just your chances were terrible to start with. And on top of it, she might be picky. So It's not causal that the use of language led to a lower probability. It's confounding. There is that driver, beauty, that affects A, what you want to see, what you want to say, and B, your probability of getting a response. And that's the exact same thing that happens in targeting. So my targeting is confounding the same way, except this time it exasperates the perceived impact. And so this is, again, as I mentioned, where the data comes into play, and there is a way of thinking about this. Also, Julia Pearl worked on that a lot. Look at this as a Bayesian framework. That's a way that data scientists look at relationships between variables as Bayesian networks, where they say there is some kind of baseline variables that affect an outcome that you're interested in. So every node here is like a set of variables, and the line means that there is a relationship, a causal directed relationship. And this is a prior assumption. That's, you have to think about this. What you want to know is how the action you take, making a compliment or showing an ad, affects that outcome. But the problem is that the same variables affect the outcome that also make you choose and take the action. If you write this down as a probabilist, then you get kind of the, this is kind of the probabilistic joint density, and you can break it up into different parts. And they are, if you look at this, again, they look an awful lot like my predictive models, right? It's conditional probabilities that we're trying. If we were to estimate them, we can identify this middle piece here. What we're interested in is the probability. What's the impact of the action? What's the probability of the conversion on the outcome, probability of Y given the action in W? We account with a model for our selection. So this is kind of us targeting. I'm not going to any more detail. All this to say, people have tried to do this for a very long time, and if anybody tells you they can prove to you that they can establish causality, I don't believe it. But once in a while we get it right. And let me convince you that once in a while we get it right. So the method here, if you want to read up, is called targeted maximum likelihood, and it's called a double robust estimator, meaning you estimate two different models, and as long as one of them is behaving halfway decent, you have guarantees, and yes, this is kind of proving stuff, you have guarantees that your model is consistent, meaning you get the right answer. I have this in for decoration. It's in the deck. You can look at it later. I'm not going to the details of how this is estimated. But again, we're basically building two separate models, one that predicts who I'm targeting, one that predicts what happens as a function of targeting and the baseline. Now, the first test I'll ask for is, what happens if I show you the wrong ad? In particular, how does an ad for a telecommunication service affect your pizza buying? How should it affect your pizza buying? Not at all. So you'd better come back, your method better come back and say nothing. And this is what you see here, that the model here, forget this part, basically says whether you see an ad or not, there is obviously some difference as always, but the p-value, meaning the significance of that difference, is completely irrelevant. We also compared it to an actual A/B test where you see the two outcomes, one where you held out and showed the public service announcement, and one where you run the algorithmic solution, and you come within very, very close. This is the probability of conversion with the ad, and this is without, and they are very close to each other. So my point being here, in this experiment, we show that the predictive modeling solution gives us very close answers to the A/B test. And then you can actually look at this and see when ads are effective and when they aren't. We used to have a product that we offered this kind of as free service. I mean, it doesn't cost me anything to build these models. And what would happen is that the account management would call me and say, Claudia, can you run it again? It doesn't look like the ad's doing anything. I said, yeah, I can run it again, but the ad's not doing anything. It will give you the exact same answer next time. So we eventually sunset it. So that's my kind of critical perks at how interested the industry really is. And one of those cases where we couldn't find anything was that. What do you think we're advertising? It's a hotel chain, obviously. So welcome to 15 years of click optimization. Yes, maybe people click on it, but they don't book hotel rooms based on that creative. Yes?
Go back about A/B testing for a second.
Yeah.
So you said that one reason that A/B testing doesn't work often is because the customer's just not willing to pay for like nonsense ads. But can you not get at the same sort of procedure simply by failing to deliver an ad to somebody who the predictive model says you should deliver an ad to, and then observing the difference in outcomes? So just don't bid on some randomly selected.
No, because you're missing out on the selection bias that you get from the bidding. Win rates typically are 15%, so who knows what the other 85 are? The short answer is no, but you see, I'm offering it for free and they don't want it. So, the last, and I promise to keep it short, when are you kicking me out? Good, I'll take 5 minutes then. A story that happened in spring 2012. In our internal KPI, just measuring how well the model worked, the median over about 100 models, the median lift doubled in a matter of 2 weeks. And if there's one thing true about data science, if it looks too good to be true, it's too good to be true. Well, usually you're happy if a performance goes up, right? But I hadn't really done anything. So what we found is these strangely predictive websites like this one, Women's Health Base. And the model suggested that people who go to Women's Health Base are interested in software, pizza, hotel chains, cars, credit cards, and the like. Right. Welcome to the world of bots who have found out how to skim money, extract money from the advertising world by faking to be a real person in these auctions. So there are people who create websites and then they hire somebody to write bots that go to these websites to then sell ads in the exchange to, for instance, me and many others. So how do you tell the difference between human and an algorithm? That sounds like an old problem. Turing had the same question. Now, the modern solution to the problem is to show captures. Now imagine I show you a capture before every ad. Yeah, okay, okay, let's look at the traffic patterns and see how this kind of web visitation jumps from one URL to the next one. And I'll skip the little puzzle in the interest of time. So what I'll show you are these connections between two sites if at least 50% of the cookie that I saw on one also show up on the other side. All right, fine. You give me 30 seconds. What website is that? So there's a website that has 55% overlap with YouTube, and then you see how the overlap goes down. A couple of new stuff in here. This is the New York Times. This is the overlap that we see between the people who go from one side to the other. How about this one? Look at this. 96% co-occurrence with what? Film annex. Anybody ever heard of this? No? Me neither. And the rest, I mean, women's health base and men's health base in close competition here. This website is called Hip Hop Havoc. I've given this talk about 10 times. I finally met somebody who has been there. So it's not purely bots, but a lot. If you plot this network, when I show you overlaps of more than 50%, this is what the world looks like. And then let's take a look at one of these small ones, and this is all about Boston. It's the Boston Herald and search about Boston. So that's probably okay. That's human behavior. What about our friend Women's Health Base? Well, it's right there. They have a lot of time at their hand, man, to serve, right? And I want to point out the very diverse set of interests. Wrestling news and This is a footprint, the digital footprint of a bot network that is generating fake traffic to basically sell ads to bots that don't see it. So fast forward in 2012. Now, why did our performance go up? So far, I'm just telling you there's a lot of traffic here. Turns out they started also visiting brands' web pages because that increased the value of the ad. Because now all the retargeting would happen when they follow you around. You look at the product and then you see the damn thing for the next 3 weeks showing up on your browser all the time. So retargeting is very profitable, and the bots now not just go to fake websites, they also go to real ones to make the bot more valuable and then increase the bidding. So when we found it, I mean, there goes my performance, all went back to normal. We started not recording this data anymore, and the performance went back down. So in the end, in the real world, it's all a matter of cheating, whether it is those who try to cheat you and you try to find them, or it's me trying to build with transfer learning models for a completely unrelated problem or a relatively unrelated problem. Thank you very much for your time and the extra 5 minutes, and some of the papers.
Thank you, Claudia. We have read already quite a few questions, but perhaps there's somebody who has one last burning point to be made. If not, then I want to kind of compliment you. I must say that just, I think you took kind of an hour to explain what your algorithms are doing in less than 100 milliseconds, which make us humans feel kind of not really up to the game. I must say, I was both distressed what's kind of happening without me knowing it, but somehow realizing that there are really smart people analyzing this made me feel slightly better. So thank you so much for being here and sharing your work.
Thanks again for having me.
Thank you.